Hello everyone, my name is Roy Jafari and I would like to welcome you to another video. In this video, we are going to talk about noise and bias, and we are going to have an ethical perspective when we talk about these two sources of errors. In this video, we are going to go as far as seeing the difference between noise and bias and see in two different possible situations how these two sorts of errors may shape the amount of errors that we have, and what are some lessons from the ethical perspective we can derive from this conversation. All right, let's look at this slide. So as we had discussed before, if you have watched one of the videos about errors, data, whatever we have, is basically a combination of true signal and error. In this video, basically what we are going to do, we are going to dissect error in two different parts. We've got random error and we've got systematic errors. Random errors are the one types of error that we don't know the cause, the reason. These are basically happen due to the inconsistencies of our tools and our measurement models, right? And the systematic errors are the one that happens because of a problem, data collection. Here, basically, the random errors are basically noise, right? So you're basically having a different sort of name for them. They're the same thing. Random errors are noise, and systematic errors are bias, right? So that's how we're going to continue talking about these two terms. So let's update our model for the data, or our equation for data, which was true signal plus error is equal data. And now we can talk about data is equal true signal plus bias plus noise, right? So always we have these two types of errors. So now, instead of having a theoretical definition for them, we want to experience what these are in first visually, then with an example, right? So when the true signal is known, we can actually, do to some extent, we can measure bias and noise, right? So for instance, this, figure, we've got four situations, and each situation we're basically reducing our measurement, or like modeling our measurement effort, like a shooting contest, or like a performance of a gun, right? So we've got this target, and if we manage to get our shooting, or we hit around this red circle, we assume that this is a good shoot. If not, that's not a good shoot, right? So we can see in this left situation, we have high noise and with bias. So the bias comes from the fact that we can see that we're supposed to be shooting a little bit left and bottom, but we are sort of like missing the mark more often than not, right? But then when we manage to reduce the bias, right? So we make sure that there is no bias, then we still are having some problem, right? So we can see that even though our bias is reduced, we still, because of noise, we have some problems, right? It's only when we've got taken care of noise and bias in the right situation that we are doing the best we can. And there are situations that we have low noise, but still we have bias, and we can see that we're still making a lot of mistakes, right? So in this sort of like figure, in this visual, we can see the difference between bias and noise. Noise is basically our incapability to be as accurate as precise as we can, and bias is that we're just getting it wrong. We are doing something else. We are shooting for something else. We are measuring something else, and that's the difference between bias and noise. But let me give you a more tangible example. So here we've got an example of 5 individuals that they were just hired by this imaginary company. And in the beginning of their starting with the company, we asked 7 different reviewers, right, to estimate the number of years that these individuals are going to be working with this company and be successful, and are not asked to leave, right? So this is just an imaginary example. And in this situation, it happens that we also know the actual numbers of years that these individuals ended up, staying with the company, right? So these are the reviewers, right? So we've got 7 reviewers, and they estimated the number of years each of these individuals are going to be staying with the company. We've got Charles, we've got Soham, we've got Nicole, we've got Basia, and we've got Rachel, right? So if we want to talk about bias and noise, we can have different angle to this conversation and to this analysis, right? We can have a bias noise investigation about each individual. For instance, we can see here that about Charles, we have some noise. This is the actual value. We've got some noise, right? So these are the noise. All right, so we see that our reviewers are like overestimating or underestimating, but at the same time, when we average the estimates, this is the average, right? When we calculate the average of the estimate, this star, then we do see that our noise becomes less, but still our collective review, the 7 reviewers, there is still a difference between the actual and the the one that we estimated. I mean, imagine we use the average to base our final decision on, and that is sort of the bias of our system about this individual. But these are the noise of each reviewers, right? So the same thing we can see about each of these individuals, right? We've got less noise in some of them, we've got more noise in all of them, right? There is less noise here, there is more noise here, and again less noise here. So this is an individual perspective, right? But we also can have a collective perspective. So for instance, here we can see if we were to make a decision by using all of the 7 individual, right, 7 reviewers, and use the average, we do see that sometimes we are overestimating and sometimes we are underestimating. We see overestimate, underestimate, and by and large we do see that we've got errors, right? So at this level, these errors are just errors, right? There is no it's not really easy for us to say if this is bias or error because we don't have much other things to draw on. But in the previous angle, here we do see that from different aspects of the reviewers, we have noise and bias, right? So the conversation about bias and noise changes, or our definition of bias and noise may change based on the situation that we are looking at the data. But we also can look at the bias and noise of each reviewer, right? So for instance, this is the reviewer 1, and by looking at this, we do see that there are some perhaps noise and biases here. I mean, it's very difficult to distinguish between them, but we can see that there is an overestimation, underestimation, overestimation, underestimation, overestimation. For instance, about reviewer 2, we do see that there is a large overestimation here. There is a large underestimation here. There is another large overestimation here. Another large underestimation and overestimation. And when we look at this specific data, we do see that, for instance, in this case, all of the overestimations are happening for white-looking individual, and the underestimations are happening for international or foreign looking individual, right? So in this case, we can see that there is some bias that it's obvious a reviewer too has. So in this situation, we can see that there is a bias, but are we going to be able to actually separate between the bias and the noise? We might sort of like do some calculation, but this is not really that much separable. We can do see that there is a bias, but we don't know exactly how much of this bias. I mean, we do expect to always have some noise, but how much of this is bias, how much of this is noise, or the same here, it's not easy to actually separate them from each other, because this is the working of someone's mind. But the point is that here we do see the bias, right? So it depends on the situation that you can see or not see the bias or the noise. You can sort of have the same type of analysis and investigation by looking at these other reviewers. So for instance, let's look at the reviewer 3. The reviewer 3, we do see that we've got overestimation here, some overestimation here, some underestimation here, some underestimation here, and again underestimation here. And then when we sort of look at all of the data, we do see that all of the underestimations happens for the gender female. All of the overestimation happens for the gender male. This could be also bias about gender, but again, how much of it is actually bias, we don't know, right? So I want you to look at these 4 other reviewers and see if there are some biases and if you can actually explain those biases, right? So reviewer 4, go ahead and do this. I'm going to put some music on this video while you are trying to figure this out, right? So have at it. So now we want to talk about in another situation, right? In the previous situation that we talked about bias and noise, we did know what was the actual data value, or we did know what was the true signal, right? But it is the case in most of the time we actually don't know, right? We don't know the true signal, right? And when that is the case, we're going to see in those situations we actually cannot really separate the bias from the noise, right? Most of the time, the reason we do estimation, the reason we do prediction, the reason we do classification is because we don't know it. Now, in advance, we want to be able to have some values that can help us for our decision making. At least in the moment, we are not going to be able to know what is our actual or true signal. Of course, we can do some analysis that do some prediction with our system and let the unknown become known 5 years down the line, 20 years down the line, or whatever, and then do some analysis the way like we did. But a lot of time it happens that we are just in that point, we don't know the true signal, right? So in those situations, investigating and understanding the bias becomes even more difficult. So for instance, in the situation on the left, we can see that the green and blue attempts have more noise than the purple attempts, right? You can see that these have less noise. We can't see this, but do we have a bias? We don't know, right? Both of them seems to be getting at the same thing, right? But because we don't know what is the actual value, what is the actual true signal, we don't know if we have a bias or not. It could be that both of them are getting at the right thing, and it could be that both of them are getting at the wrong thing. And because of that, we just don't know about the bias. How about in a situation that there is some differences or there is not some differences, doesn't really matter, with the noise, but we do see that they are getting at different things, right? We can see if our measurement are sort of like getting at the same thing or not, right? Here the measurements are getting at the same thing, but here they're not. In these situations, we do know that one of our measurement system or one of our models do have bias, or both of them, right? So in these situations, we have a little bit more information about the bias. At least we do know that one of them is biased, or both of them. But still, we cannot really know which one has bias, right? So let's update the previous example, but this time, let's assume that we don't know, the actual values. And when we don't know the actual value, being able to calculate the bias becomes even more difficult, right? So here, we don't know the actual value, and this is the sort of like the wisdom of the collective wisdom. We do see the noise, but is this the right answer or not? Is this the what we need to do? I mean, it would be wise to draw our sort of like decision based on the collective wisdom, but is it the actual value? Do we have bias here? At least when we are sort of like doing it in the once chart starting with the company, we don't know if we have bias or not, right? So the same thing for all of these individuals. We do see that we have noise, but we don't know if we have bias, right? So that's one of the first things we want to learn. The second thing is, again, do you remember once we looked at all of the data, when we knew the actual values, we were able to see if the system that we use as an average have bias or not, or does it have overestimation or underestimation for certain profile or not. But here we don't have that luxury. We just don't know if there is bias or not. We just see that there are some variations, and this variation could be just natural to the system, right? So in those cases, we're not going to be able to know if there is bias. How about if we were to for instance, compare reviewers? So for instance, here this is the reviewer 1 and this is the reviewer 2, and then this is the reviewer 1 and 2. Now we do see that these reviewers are getting at different things, right? So certainly they're not getting at the same thing. There is some bias here, but which one has bias? Which one is more right? Is it in the middle, or is it like a little bit toward the reviewer 1 or reviewer 2? These are the things that we just don't know. We just know that at least one of these reviewers have bias. And we did see when we had the data, number of years these individuals stayed with us, we did see that reviewer 2 had more bias. So before ending this video, I wanna mention a few things that are going to be fundamentally important when we have we are going to rely on the results of our measurement models or our analytic models, right? So first of all, we say data is equal to true signal plus bias plus noise. This is the model that we have, but at the same time, prediction, whatever algorithm you use, again, it might be, the error might be bias plus noise, right? So you want to be able to sort of like see, based on the situation, if you can sort of like have some information about bias and noise to see where things are. Are both of your algorithms doing the same thing? Is there some bias in your system or not? So that can be valuable when it comes to decision making using these models. Or if you can, down the line, sort of do some investigation to see some biases in your decision making or your algorithm, you wanna be able to also use this model. And also the same thing about classification, bias and noise. So it's not just about our measurement models or our data. Our prediction or classification could also and do have errors, and the errors for them can be a combination of, is a combination of bias and noise. The last thing I want to leave you with is that we saw in this video that calculating bias is more difficult than capturing and calculating noise. Sometimes in different situations it might be impossible actually to do that. And we do know that if we manage to reduce errors, bias or noise, it's good, it's improvement. So a lot of times we might have an urgency to feel an urgency to address bias, but sometimes it's not possible, or sometimes it's difficult. But at the same time, if we were to reduce noise, which is more attainable, especially with these algorithmic way of decision making, machine learning, and data mining algorithms, one of the key features, one of the key way that they can help us is actually by reducing the noise in our decision making.